this lecture, we will talk about different types of memory that are used by computer systems and how to read from and write to the EEPROM that's on board the PIC 16F887. So the PIC 16F887 that we've been using all semester has three different types of memory. It has flash memory, and that is where your program gets stored. It has RAM, that's where we've been using, that's what we've been using for our variables. And then we also have EEPROM, which till this point in the class we have not used, but we have mentioned as a way to store some non-volatile data. So if we look at the overall PIC memory organization, this is figure 1-2 in your data sheet. What you'll notice is there are several different locations where there's memory. So this up here is your flash program memory. That is where all of your code is stored. And you have 8,192 individual codes that can be written there. Those are 14 bits wide. You also have RAM, and in this particular PIC we have 368 bytes of RAM that are usable for us to store variables and any other temporary information. And then you also have 256 bytes of data that can be stored in the EEPROM. So if we zoom in on this, here you see 8192 for the flash program memory, 368 bytes for the file registers in our RAM, and then 256 bytes of data in the EEPROM. So if we look at what we have, your flash memory, you have a lot of flash memory because you're going to be writing quite a bit of code and you want to be able to do a lot of things. You generally don't have as many variables as you have lines of code, and so you have 368 bytes of RAM, which is actually at the top end of this particular PIC family. Some others have actually fewer spaces where you can store some data. And then we haven't used our 256 bytes of data, but we will over the next day or so. Flash memory, the good thing about that is it's non-volatile. So you've probably noticed as you've taken your trainer kits home or taken them to the lab back and forth, if you turn them off, they still maintain their program memory. That's good, so we don't have to keep reprogramming every time we want to use it. And you can also protect the code using code protection. So that way, if you do certain writes to it, it's not going to overwrite the code. But generally, when you reprogram it, it is completely erased and then reprogrammed all at once. You may have noticed when you're using your programming software that you don't have to just blank the code. It automatically does that for you when you say load and program. So how do you store the program into Flash? Well, what happens is when you're using MPLAB-X to compile your code, whether that be in assembly or in C, it gets converted into a hex file. And we've really just ignored the details of what are in those hex files until now, but now we're going to unpack that and look at what happens. So every command that you wrote in assembly gets translated into one 14-bit opcode. And that 14-bit opcode represents different things. So depending upon what command it is, it might simply represent the command. So something like clearing W, that's all it represents. If you are moving a literal value into W, it might also contain a literal value. You might also have information about the destination of the result there. So if you are putting something into W or back into a file register, you might also have, for bitwise commands, information about which specific bit you're testing, setting, clearing, all those types of things. And so if you look at page 236 in the data sheet, that does show all of the different opcodes, and you can see how your different assembly commands get translated into these different binary values. So let's take a look at the code organization. So the 14 bits contain usually, in some cases this would be bit 8 through 13 if you have a byte-oriented command. If you have bit-oriented commands, then it's just 10 through 13. If you have literal commands, then you have 8 through 13 for the opcode. And if you have things that skip, like calls and go-tos, the opcode itself for the command is 11 through 13. And then in the case where the results go into a destination of either W or F, you have a bit there. Bit 7 is going to hold that destination, so that's that 0 or 1 that we've been putting in. And then this is going to be the bytes that are the memory location of the particular register that we're talking to. And so in this case, we can determine, let's say it's tris A, let's say it's port B, or whatever it happens to be. Each of those special function registers has a memory location. And so the memory location, which you can look up in a table, will be what is put in 0 through 6 here. So in this case, let's look at the different opcodes. This is the part of the table that we haven't talked about thus far, is the 14-bit opcode. So if you are doing ADDWF, then these bits correspond to ADDWF. You have 00, 0, 1, 1, 1. And then, remember, it's ADDWF. You put the name of a particular register, and then you put a destination. So the destination goes next. If you're putting the result into W, that would be 0. If you're putting the result back into that register that you're referencing, it would be 1. And then you put the address location of the particular special function register, which you can look up in the data sheet what address corresponds to all your different ports, your different intcon, or whatever it happens to be that you're dealing with. And W with F, here you can see a different opcode. Each one of these commands has a unique sequence of bits up here in the 14-bit opcode. You'll notice that all of the byte-oriented commands start with 00 as the leading 2 bits. So if you are given 14 bits and you have a 00 leading in there, it's a good chance they are a byte-oriented command. If we go on to the rest of the table, these bit-oriented commands, their leading bits are 0 and 1. And in this case, you've got 3 bits that correspond to the specific bit number. So if you're talking about bit clearing F, then this gets translated, the first 4 bits are going to be 0, 1, 0, 0. And if you're talking about clearing, let's say, bit 2, then BBB would be 0, 1, 0, or binary for 2. And then F is going to be, again, the address for whichever register that happens to go into. So if it happens to be port A, then you put in the address where port A is located. If it happens to be tris B, you happen to put in the address for where tris B is located. And so you've got that. And then down here, you've got your literal and control operations. And so those are things like calls, go-tos, some of your logical operations as well, where you've got inclusive ORing literals with W's, your various types of returns, all those different things, and they have different leading bits there. And so in this case, you've got here you're adding a literal with W, and so you're putting in add literal with W. The leading 5 bits are all 1s, and then your literal is going to be 8 bits. That's going in this K over here, and then this particular bit is going to be a don't care. So you do have a few don't cares in there as well. But generally, this is the structure of the opcodes. RAM is volatile, so anything that you store in, say, a counter or something else like that is going to go away as soon as you cycle the power, which is probably useful. A lot of times we want to clear some of those variables when we are wanting to run our code again or just starting again from the beginning. The nice thing about RAM is it offers very quick access. So if we just need to write something quickly, let's say a counter, and we're cycling through, it's going to be a lot faster to increment that counter if it's in RAM than it would be if it's in EEPROM, and we'll see exactly why in just a little bit. But in this case, you simply declare variables using the different addresses. So typically, we've used those EQU statements in assembly. In C, those memory locations just get chosen for us by the compiler. But you've actually got some RAM space in each of the banks. Most all the RAM space that we've been using for variables has been in bank 0, which is quite convenient for us because most of our operations tend to happen while we're in bank 0 once we get all of our configuration done. And we have 96 bytes there, which for all the code that we've done thus far has been plenty of variable space for what we've been doing. The EEPROM is short for Electrically Erasable Programmable Read-Only Memory. That is non-volatile, so anything you store in EEPROM, as soon as you cut the power, it's still there. But the trade-off there is that it is slower. You can read and write individually 1 space at a time, so you're going to need an address and some data, and then you can write to it. You can just get an address and read back 1 byte of data at a time from the EEPROM. Let's look at how that works. There are actually several different registers that are associated with sending and receiving data to the EEPROM and also the program flash memory. And depending upon whether you're writing to EEPROM or the flash memory, you go through a very similar sequence, but it's a little bit different. EECON1 and EECON2 are your configuration registers there. EECON2 is sort of a funny register in that it's not a regular register per se, but there are a couple values that you have to write to it in order to get permission to access either the program memory or the EEPROM memory. EEDAT and EEDATH is where your data gets stored, either to be written out or as it's read back in. And EEADR and EEADRH are where your address gets put in there if you're trying to either read from or write to a particular location. EECON1 has several different things in it. EEPGD is perhaps the most important bit. It determines whether you're writing to the program memory or reading from the program memory, or whether you're writing or reading from the EEPROM data. So you can actually rewrite your program while you're running the program. So that allows for training. You can think about artificial intelligence, genetic algorithms, where the algorithm actually trains itself, and that's quite useful as you learn something like user preferences, or you have a robot that's learning to navigate a course. You can actually change the algorithm on the fly, but you have to be very, very careful about that. If you're writing to or reading from the EEPROM, then you put 0 there. Bits 6 through 4 don't do anything in this particular register, and you've got an error flag if there happened to be an error with the EEPROM write or read. Bit 3 would get set right there. And then WREN is what allows you to write to the EEPROM. That bit will have to be set. And then depending upon whether you're writing or reading, well, it gets set if you're writing, but depending upon whether you're writing or reading, you also will set the WR or the RD bit accordingly. EECON2 is effectively what I like to call the Mother May I register. And so if you want to write to the EEPROM, you have to put the specific sequence 55 hexadecimal and then AA hexadecimal, and then set the WR bit. Basically what that does is it ensures that when you're writing to the EEPROM, you really meant to write to the EEPROM, so you're not just accidentally overwriting your data. So the PIC has this control sequence that you have to go through. Otherwise, you may just accidentally write to the EEPROM. This actually makes it a little bit more challenging. And as far as I know with this particular PIC, that's the only thing you ever really write to EECON2. You can't read it. If you do, you'll just get all zeros back, but it won't give you a value. And so the only thing you ever write to it is this 55 and AA. EEDAT and EEDATH is where the data goes. If you're talking about writing to the EEPROM, you only use 8-bit data. So they're 8-bit registers, 8-bit data, and so EEDATH is not used at all. That is only used if you're talking about program memory. But if you're talking about writing or reading from just the EEPROM, you just use EEDAT. You will not use EEDATH. And just like you have data, you also have an address. And similarly, since we only have 256 locations in the EEPROM, we only need EEADR for using the EEPROM. But if we are talking about writing to the program memory, remember you've got 8,192. So if you're reading or writing from the program memory, you will also need the high byte. Really, you're only using the lower 5 bits of that because you've got 14-bit addressing. Remember, the program counter is 14 bits because 2 to the 14 is your 8,192 for each of the entries of code that you can put into this particular program. So, how do you read from the EEPROM? It's actually fairly simple. You just put the address in the EEPROM that you want to read from into EEADR, so that's a number between 0 and 255. So if you want to read from memory location 4, you put 4. If you want to read from the first memory location 0, put 0. And then you clear EEPGD. Remember, that's what's saying we want to deal with EEPROM data, not program data. And then you just set the read bit. So you don't need the write control. We're not writing to it, but we're just reading it. And so we set the read bit, and then after a clock cycle, that data will be in your EEDATA or EEDAT register, and you can just read that and process it. You put it out to display, whatever you want to do. How to write to the EEPROM. This requires a little bit more detailed sequence. You want to first make sure that there's not something else writing to the EEPROM, so you should poll the WR bit to make sure that there's not a write currently happening. So you can just put in a while WR, just like you did with the go bit for the A to D. And then you want to put the address that you want to write to in EEADR. And then you want to write the data that you want to put out in EEDATA. Then you're going to clear EEPGD. Again, that is what determines you're dealing with EEPROM data. Then you want to set WREN. That basically gives you permission to go ahead and write. You want to turn off any interrupts because you don't want to get interrupted partway through a EEPROM write. So you can just clear the GIE bit if it happened to have been set or you're using interrupts. And then you want to do this mother may I sequence. So write 55 hex to EECON2, write AA hex to EECON2. Then you want to set the WR bit, which actually says, okay, go ahead and do the writing. And then after it's done, then you can go ahead and enable the interrupts again. And you can handle this either with an interrupt service routine. There actually is a EE interrupt, one of your peripheral interrupts. Or you can just poll the WR bit, and when it goes back down to 0, then you know that that writing is done. Reading from the program memory is pretty similar to reading from the EEPROM. The only difference is now you need a few more address bits. And then the other difference is in your EEPGD, that particular bit is going to be set instead of cleared because that's what determines program memory versus EEPROM memory. And so for the address, you're going to use actually both bytes there. And then after you set the read bit, you'll want to wait 2 clock cycles. So you can actually do ASM no op just to do a couple no ops in there, waiting a couple clock cycles so you have enough time to get back both of the registers filled with your data, and then you can read the data in EEDAT and EEDATH. Writing to the program memory is a little bit trickier. Generally, we write things in 8-word data blocks. And so in order to do that, you use what is called indirect addressing, and you'll access 8 words of data at a time just to be written out. We're not going to do that in this course, but I want you to be familiar with it. And there's actually an example on page 123 in the data sheet. Example 10.4 talks about how to use indirect addressing to write to the program memory. Just in case you ever had to do this, your FSR is where you store the address that you're trying to write to, and then INDF is going to contain the value for the data that you want to store at that particular location using FSR. You can think of FSR as basically being a pointer to the data that's in there. So it's basically an address that is identifying this is where the data is going to go. INDF would be the data. So you don't really have to worry about doing that as part of this class. I just wanted you to be aware of how that is done if you ever have the need for genetic algorithms, artificial intelligence, things like that in the future.